Why did you want to be an astronaut?
Actually, I'll correct you. Many people have asked me that question, but it may be the first time I get to tell you the answer. I believed growing up that we would all be astronauts by the time I was, an adult. That's not true, obviously, and we're not as advanced as I thought we would be. But I believed when I was young that that would be my place for some period of time in my life, was to do that. And I think when I went through university, I'm a geologist, a geophysicist, and I thought, well, wouldn't it be great if I learned about rocks, minerals, and geology, and then we went to the moon and I could help, utilize resources on the moon because of my geological experiences and background. So those were the things that interested me, and I was always interested in jets and flying and watching the Apollo guys walk on the moon. Those were the things that interested me and that really caught my attention. So I just thought that we would all, as a race, be advancing to where it was standard for people to be spacefarers, space explorers.
I want to get you to take us along that course, but first let's start at the beginning. Tell me about your hometown. Tell me about where you grew up.
Okay, so I grew up in Lake Orion, Michigan from the age of 10, which is a suburb of Detroit. And before that, lived in Royal Oak, Michigan, also a suburb of Detroit. Lake Orion was a little farther away. Have fond memories of summer and winter. I think winters were quite enjoyable. We used to do a lot of snowmobiling and snow skiing, and in the summers we spent our time water skiing. And being a suburb of Detroit, Motor City, I became interested in automobiles at an early age. My father and uncle were both engineers at Ford Motor Company, and so when you grow up in Detroit in the Motor City and everybody works for the auto industry, you, I think, have a natural affinity to like vehicles and cars, and raced motorcycles at a young age, raced bicycle motocross at a young age, and raced go-karts for a number of years after I got out of high school. So I was always interested in doing those things, mechanical things, and worked as a mechanic at a shop outside of Detroit. So that's sort of what my childhood was like. It was doing all those fun things, but a lot of it revolved around motorsports and working on mechanical objects.
That place and those people had a real impact on the person that you turn out to be.
Yeah, I think so. Yeah, very directly. Yep.
Did you get a chance to see it on your last flight?
I believe that the time I've spent in my life working with tools and familiarity with tools in that environment allowed me to be at ease with the things I was doing, working with my hands when it came to that. Not so much with the spacewalking stuff, because that's new to everybody, but I didn't have to focus as much on the actual tasks themselves. I mean, clearly they were important and critical, but it didn't require as much of my concentration, and that allowed me to expand it to understand what else was happening around me, like the fact that the Earth was spinning below us and we're traveling at 17,000 miles an hour above it, and all those things. It gave me a little more time to appreciate that, I think.
What kind of view did you have of home from space?
Well, it was pretty good. On STS-125, we were 300 or so miles up, which is roughly 100 miles higher than where the space station flies. So we had a broader view of the Earth. Unfortunately, because of the orbit of Hubble, we stayed fairly close to the equator of the planet. So we were roughly 25 degrees on either side of the equator, whereas a space station mission goes all the way up to 55 degrees. So whereas a space station will fly over parts of Canada, on the Hubble mission, we really didn't get any farther north than Cocoa Beach, Florida. That was it. So the view is higher and broader, but we don't ultimately see as much of the planet because we don't fly as high north and south of the equator.
Didn't get a chance to look straight down at.
Right. You see things at a very oblique angle, which was also very beautiful, because some of my best memories of space, I have I've had really 3 or 4. And one of the best ones was during a spacewalk, flying over just about New Orleans and looking north and seeing Michigan, you know, my home state. I could see it in the distance, and it was just beautiful. It was really a slight angle, so I could see the Great Lakes, and it was just falling into the shadow, you know, of darkness. But it was just a beautiful, beautiful sight. I thought, hey, that's pretty neat. That's my home, you know, that's my state. I can see, you know, where I grew up practically, or at least whereabouts. And one of the other great memories was flying over Houston. And my first EVA, right at the end of the last, you know, right at the end of the spacewalk, on the robotic arm, but I was facing the Earth, and the shuttle was behind me. So there was nothing between myself and the Earth except my visor, and just looking straight down at Houston. I mean, I could see everything. I could see, you know, maybe I couldn't see it, but I certainly could identify where Beltway 8 was, and 610, and all the freeways leading in, you know, and I could clearly look right down at Clear Lake, where, you know, my house would be just about. So that was pretty neat. And then Hawaii, seeing Hawaii from space was pretty spectacular. Good vivid memories of that as well.
You touched on this. Let me get you to tell us, sketch out your educational and your professional career that led you to be here, to be an astronaut.
I left high school and stayed home. I went to Oakland Community College for 3 years to get a degree in geological, well, it's an associate science degree, a 2-year science degree. I did that in 3 years, specializing in geology with a minor in industrial design. So you could say I was pursuing 2 careers, one as a scientist, one as an automotive designer. And those are the 2 things I wanted to do, and I chose the scientific path over the, I guess what you could say, artistic path. But while working, or while going to school at the community college, I also worked as a automobile restoration, you know, mechanic in a shop. It's called International Auto Works, and we restored 1950s Jaguars, and that's all we did. We get these cars in and strip them down to just the frame and the shells, and send them off for metal stripping, and then we would just slowly rebuild those cars with new pieces and parts and make vehicles out of them. So that was, you know, a 3-year job while working and going to school at the same time. I worked a few summers after that, but once I left Oakland Community College, I went to Purdue and pursued a bachelor's degree in geophysics, or solid earth sciences, so still geology, but with a specialty on geophysics, which is sort of like the physics of the Earth, or using physics to sense what's, you know, underneath the surface of the Earth. And so with the credits from Oakland Community College transferred to Purdue, I spent 3 years getting the other 2 years of my degree for a bachelor's degree in geophysics. Stayed there to do a master's degree in geophysics, and then went on to Queen's University in Kingston, Ontario for my PhD in seismology. And there I studied underground mining seismology, and spent some time working in mines in Canada and in the US, installing seismic monitoring, or what you could consider earthquake monitoring systems in underground mines. So you know, that was a 4-year program for a PhD. Worked a few years after that for a small engineering consulting firm in Kingston, Ontario, and then came down to Houston to work for ExxonMobil Corporation as a geophysical operations specialist, and you know, doing oil and gas exploration here in the U.S. and actually worldwide surveys. That lasted about 3.5 years. And in 2000, I was selected as an astronaut. So it's been 10 years since that point, and here we are on the second flight, STS-134. And
the flying in space part of your chosen career is one that we know has a possibility of dangers. So I need to ask Drew, what is it that you think that we're getting as a result of flying people in space that makes it worth doing it?
I think it's just that. It's flying humans in space. It's flying us off of the planet. It's considering the possibility of a different home besides Earth, ultimately, for the human species. I think for humans, it's always been about what's out there. Are we alone? Could we be the only ones in this infinite universe? And I think the only way we're going to find out is if we keep pushing the boundary and trying to get out there. And this is just the beginning. I mean, we're barely getting off our own planet. But someday, you know, if we continue this and technology continues, and as we get smarter or better at adapting to the world around us and the universe around us, we will be traveling, you know, throughout the universe doing amazing different things. And so I think why is it worth it? It's worth it because we can, and we're capable, and we're getting better at it. And someday it'll be just like I thought it was supposed to be when I was a kid, that we all fly in space all the time and travel through the universe.
You're a member of the crew on Space Shuttle mission STS-134. Drew, summarize the overall goals of this flight and tell me what your job's going to be.
The overall goals of this flight, that's a pretty big question. I'll try to summarize it. Our main payload is the alpha magnetic spectrometer, which is a science payload that we're carrying in the shuttle to place on the external truss of the space station. That's a payload it's a $2 billion payload with 16 countries participating and some 500 scientists that have worked over the past probably 20 years to develop this experiment. And it's a follow-on to AMS-1, Alpha Magnetic Spectrometer 1, that flew on Space Shuttle early on. So this is a follow-on experiment to that, but it will be permanently placed on the space station to hopefully collect data, high-energy particle physics data, for the remaining life of the space station. So that is our primary payload. We're launching 6 crew members to space, all males, 1 European astronaut, Roberto Vittori, and during the mission we'll do 4 EVAs now. None of them are associated with AMS, but they all are, I guess, what you could call standard space station repair or maintenance EVA activities. Yeah.
All of your crewmates have been to the space station before. All 6 of you, of course, have flown in space before. 2 of them have actually done long-duration missions on the station. Does that benefit the group in getting prepared for this flight?
I think so. Yeah, we have a unique crew in that sense. So if you look at the makeup of our crew, we have 3 space shuttle flyers, myself, Mark Kelly, and Greg Johnson. Greg Shamatov also flew on Space Shuttle, but not as a crew member. He was flying up to do his long-duration mission to spend 6 months on station. Mike Fink has never flown on a Space Shuttle, but he's lived on Space Station for a year, but only flown on the Soyuz vehicle. Roberto Vittori's made 2 trips to the space station, but never for long term. So I think maybe he spent a week at a time up on the space station, also only flown with the Russians. So there's a lot of experience, but we have varied experience. And I myself have never seen the space station. I've only flown to Hubble, which is a completely different type of a mission. So for all of us, although we have a lot of experience, very few of us have the same experiences. So that has benefited us in many ways preparing. So everybody has a different way that they approach tasks and objectives and also problems, and I think that's been a positive thing. There's been a lot of growing pains with us, or learning about each other and the ways that we've done things in the past and all of our experiences, but I think overall it's made us a stronger crew with more ways to approach problems.
Well, let's talk about some of the cargo that you're bringing to the station. Start with the Express Logistics Carrier 3. Tell me what that is.
Express Logistics Carrier 3, we call it ELC 3. It's one of 4 that will live permanently on the space station, and essentially they are storage shelves for spare parts for the space station. One of the components on our Express Logistics Carrier is a robotics arm called SPDM, a Special Purpose Dexterous Manipulator, I believe. And what that allows the Canadarm2 that lives on space station to do is perform tasks that are normally done by spacewalkers. So it gives it, in a sense, arms and hands, and allows it to carry out activities that we would normally do, but over a much longer period of time with significant input from a ground control team. So that's one of the components. That's probably one of the main components that we see on our ELC component. But overall, those pieces are, spare parts racks for the space station.
So what does it take for you and your crewmates to install it, get it out of the payload bay and up on the top side of the truss we're going?
It's robotically installed. There are no EVA activities associated with installing an ELC rack, and what we do is use the Space Shuttle Canadarm to lift the component out of the Space Shuttle payload bay and place it in a position that allows Canadarm2 from the space station to come over and grab a hold of the ELC, and we call that a handoff, and then they take it and move it on to its permanent location on the space station.
The other major component that's riding up in your payload bay is the alpha magnetic spectrometer. You touched on that a moment ago. Tell me more. Tell me about what this does from its perch out on the station's truss.
I'll give you my best description as a non-particle physicist, if I can. It's a fairly large component. It is roughly the size of the payload bay in diameter, which I guess makes it about 12 feet across or so. And it's sort of round, shaped like a donut. You can think of it as that. And its job is to detect particles, cosmic rays and particles in space that pass through the magnet. And the magnet's function is to bend the particles as they pass through the middle of this donut to help detect or characterize what those particles are. And AMS is designed to look for dark matter in the universe, which essentially makes up 70% of the universe. We believe it does, based on estimates of planet sizes and stars and gravitational pull. The way we understand it, we think there's a lot more matter and energy out there than we can see, dark matter and dark energy. So AMS's goal is to characterize those high energy particles and try to determine which of those are antimatter, and specifically I think it's tuned to anti-helium and anti-carbon. And then also to look at, so to characterize each particle that passes through it based on its mass, its charge, and its total energy. And so there's a series of detectors, kind of like a cake, built like a layer cake inside that device, that as the particles pass through the middle, each of these layers has a different function to help characterize the mass, the charge, or the energy of that particle that's passing through it to determine what it really is. The advantage of it is that on Earth we build particle accelerators and try to, with magnets, accelerate particles around a ring and eventually smash those into a detector or another particle to make new particles. But we really can't reach the level of energy that's desired, and in space we have very high energy particles that are always present that don't get attenuated by the Earth's atmosphere or magnetic field. So this is sort of a raw, original place to measure these. We call it like an in situ measurement of these high energy particles. So that sits out there on the space station truss, and these high energy particles with very high velocities, faster than we can accelerate them on Earth, are passing through this detector at all times, and then we use the different layers in there to characterize what those particles are. So it's something that we believe we can achieve on Earth in terms of creating the particles to then characterize what they are.
I think the next question, though, is why? Why do we want to detect those particles? What's the significance of what it's looking for?
Well, that's sort of a philosophical question. I mean, that's a question of science. Why do we explore anything? So it's, in a sense, it's exploration of the universe, and it's a way for us to help determine what is out there. What is the universe made of? Where did it all start? Similar to what Hubble does. Hubble telescope, looking back at the origins of the universe, by characterizing these particles that we can't see, we can't detect, we can only infer on Earth. By trying to search for them in space, we may better define and understand, what is the makeup of the universe, what is its origins, how did it develop, and where is it headed.
So that's the only significance, huh?
Well, that's the significance that I can relate to. I'm sure there's much, much more, but it's an important experiment, yeah.
Talk about the procedure. How does AMS get out of the payload bay and into its position?
AMS is positioned similar to what the ELC pallet is, or really any payload that flies to space station in the back of the shuttle payload bay. So we use the shuttle's Canadarm to lift it out of the payload bay, and Canadarm2 comes over and picks it up and does a handoff and places it up high on the truss. And in particular, it's sitting on an inboard location of one of the starboard side trusses. So if you're looking at the front of the space station, it would be on the left, on the top of the truss.
Which is presumably where the cosmic rays are coming from.
Well, you know, I'm not so sure that it matters where it's positioned. That happened to be the best position from a thermal standpoint and also an available place to put it, because of course those particles are coming from all different directions really up there.
Plan for this mission, as you said, calls for four spacewalks by 3 teams of spacewalkers. What's your role in this group activity?
So we do have 3 teams of spacewalkers, and I was fortunate to be assigned as EV1, or the lead spacewalker on this mission. And I'm heading up a team of 2 others, Mike Fink and Greg Chamitoff, both who are long-duration space station members. Greg has not previously done a spacewalk, so he's really looking forward to this opportunity to do 2 spacewalks on the mission. And Mike Fink will be working together with Mike on the 3 other spacewalks for the mission. So EVA 1 is myself and Greg Chamitoff. EVA 2 is myself and Mike Fink. EVA 3 is myself and Mike Fink, and then EVA 4 is Mike Fink and Greg Chamitoff. So that's the way it's playing out, and it's you know, it's interesting to lead somebody. Mike Fink was a commander of the space station, so as a lead spacewalker, it's interesting, and I think it's neat for us to work together. I mean, he's a former commander, and I'm sort of the lead EVA spacewalker. So there's a lot of great information that's built into that team. You know, we've all got a lot of experience. He's done, I believe, 6 Orlan EVAs in the Russian spacesuit. So he has spacewalking experience, just not in a U.S. spacesuit.
And during the spacewalks, the one of you that's not outside is going to be running things inside.
That's right. The person who's not outside is I guess you could say the quarterback, or the you know, the director inside, working from the shuttle flight deck, reading the choreography of the steps, and you know, trying to keep us on track on the timeline, telling us which tasks are next, and how to carry on.
And it keeps all of you familiar with all of 4 EVAs.
Yeah, it does. It really helps in that sense, because, and we've also cross-trained in the neutral buoyancy lab as well, so we all have a good understanding of what the spacewalkers are going through, and as spacewalkers, you do need to have some appreciation of what you're putting the IV crew member, or the quarterback inside through, because there are a lot of tasks, there are a lot of activities. We're not always working in unison. Sometimes we get split up, and so the individual inside is responsible for the 2 of us and keeping us on track, and also coordinating with ground control. So there is a significant amount of effort that goes on inside the space shuttle, trying to keep the people outside, you know, working productively and not getting behind them, so that things can keep moving.
Let's talk about what's on the plan, at least as we talk today. First spacewalk, you and Greg are outside. What's on the plan for EVA 1? So
the big plan, EVA 1, the first couple of objectives involve the MISSIES, which are experiments, static experiments. Some are powered, some are not, that sit out on the space station trusses and are open to space, and they essentially capture space particles as well. Not in the same way that AMS does, but they have exposed surfaces in those. They sort of call them exposed facilities. So they have materials, they may have different materials in there, or metals, or fabrics, or gels, or whatever, that they're either looking at the effects of space on those materials, or actually trying to capture, you know, little particles for later analysis, you know, within gels or some material like that. So on the first spacewalk, Greg Chamitoff and I will go out and retrieve 2 that have been out there for, I believe, over a year, or about a year or so by the time we get to them, and then we'll place two new ones out in those same locations. That's first, and then what's next for us on that day is to set up for EVA 2, which involves filling ammonia back into one of the radiators that has leaked out over a number of years. So we'll spend EVA 1 preparing for those activities on EVA 2. And then we'll end the day with work on the U.S. laboratory and node section, where we're laying out some wireless antennas that are actually designed to communicate with the ELC pallets. And these are new antennas. So there's some wiring and cabling involved with that that takes up the last couple of hours of that EVA.
Let's give you an opportunity to crawl around a significant portion of the station?
It does. We'll be traversing from one end to the other of the space station on just about every EVA except for EVA 3. And that'll be new for me because, of course, on the Hubble mission, we lived in the back of the payload bay, and Hubble wasn't very far. And on the space station mission, you spend get a lot of mileage out of the suit.
2 days after the first spacewalk, Mike and Greg are swapping places, and for the second EVA.
Mm-hmm.
What are the jobs for you outside on EVA number 2?
So Mike Fink and I go out on EVA 2. Mike Fink comes out the door first. We call him essentially EV1 for the day, and we each take turns, leading each day's activities. So we go out on EVA 2, and that whole day is really dedicated to two things: filling the port radiator with refilling one of the port radiators with ammonia, and lubricating the solar array rotary joint on the port side of the space station. That's something that's been done in the past. We have, in history, 3 or 4 times now, I think, actually rotated the solar array rotary joints. And that involves removing some covers and using an actual grease gun with some special lubricant to provide grease for this bearing surface that rotates in space. And then the ammonia fill is also a very time-consuming job. Not a lot of work to do aside from opening and closing valves and mating and demating ammonia lines, but that in itself is fairly tricky and wrought with peril. So we will do our best. We've trained hard for that activity, and we'll do our best to not let any ammonia leak out, because if it does, that involves some other actions on our part to allow that ammonia to what we call bake out or sublimate off of the spacesuits before we go back inside. It's not a substance we like to take inside of the space station with us.
Is that lube job on the rotary joint not exactly what you learned as a kid working on cars, was it?
Well, it's probably exactly what I learned working on cars. Right? The grease guns look the same. It looks like a caulking gun, but the concept is the same. I mean, and I think all of us understand that pretty well. What we're trying to do. Carrying out is always a little bit more challenging in space.
For a while now, when spacewalks done on the station, prior to the spacewalk the night before, spacewalkers have camped out in the airlock as a way to get their bodies ready to fight against any decompression sickness.
Right.
Before the third EVA on this mission, you're looking at trying out a different pre-breathe protocol. Tell us a little bit about what this new procedure is.
Right, so we were introduced to a pre-breathe option by Mike Gernhardt, an astronaut in the Corps, and it's called the In-Suit Light Exercise Pre-Breathe Protocol. We call it ISLE, I-S-L-E, for In-Suit Light Exercise Protocol. And it offers us, as you mentioned, what we typically do for a space station mission is we camp out in the station's airlock at a lower pressure to allow our bodies to purge the nitrogen that's in our blood stream. And then in the morning, when we wake up and start to prepare for the EVA and have to allow other crew members to come in to help us, we have to put on oxygen, 100% oxygen breathing masks, and maintain that oxygen seal around our face so that we don't introduce more nitrogen back into our blood. We have another option aside from camp out, which is called exercise pre-breathe protocol, which doesn't involve capping out at 10.2 psi overnight in an airlock, but involves us waking up in the morning, donning an oxygen mask, and riding a bicycle for 10 minutes at a fairly high level of exertion to get the 100% oxygen flowing through our blood, and then purging that nitrogen by doing exercise. And now we have a third option, which is called the In-Suit Light Exercise Pre-Breathe Protocol, which involves us having a normal sleep period the night before, waking up in the morning, and then donning the spacesuit, so getting into the spacesuit like we normally would, and then decreasing the pressure in the airlock and having the suits at that nominal pressure, and then performing exercise in the suits. And it's not really exercise as much as it is just moving your arms and legs for a certain period of time. So now you've got the advantage of you're on 100% oxygen and you're at a lower pressure and you're exercising. So we're sort of combining the the airlock camp out pre-breathe with the exercise pre-breathe with the suit itself.
And you're already in the suit.
And you're already in the suit, right. So that sort of avoids exercising on a bike or camping out overnight. It just puts you in the suit, starts you moving your arms and legs while you're breathing 100% O2 at a lower pressure, and all those things combined allow us to go out the door and have, as you mentioned, better protection against decompression sickness symptoms while we're outside working at those lower pressures.
Is the activity in the suit normal pre-EVA activities, or is there something special that you have to do?
It's a little bit special. I had somebody tell me today, one of our suit trainers, she mentioned that we're going to do the hokey pokey in the suit. So pretty simple activities. We're just gonna move our arms, move our legs a little bit, and try to get the blood flowing a little more than we normally would, and sort of wait there and purposely do it. So it's really not much more than the things you would normally do, moving your arms and legs as you get into the suit, but it's purposely taking those actions to ensure that you've covered yourself and provided that level of protection against decompression sickness.
Okay, the plan is to do this before the third spacewalk, which is you and Mike going back outside.
Which is Mike and I, yep.
What are you going to do
Well,
outside for number 3?
EVA number 3 was a late add, so we've been training for about a year now together, and all along up until probably a month and a half ago, we had been training 3 EVAs, and we've just added this 4th EVA. And this involves installing a power and data grapple fixture, or a base for Canadarm2. So the Canadarm, space station arm, has a capability of walking around the space station from end to end to do different tasks. The Russian segment doesn't really have any of those bases for the arm to walk onto. And this is an opportunity for us to actually attach one of these base station mechanisms onto the what we call the FGB, or functional cargo block, portion of the space station, to allow the arm to walk onto that position and do some tasks in areas that it wouldn't have been able to reach previous to this. So this is an activity that's been on the book, I believe, on the books for a number of years, and hasn't found a home, and we think we found an opportunity to do it then on our mission. The advantage to doing it on our mission on EVA-3 is that Mike Fink has spent a considerable amount of time on the Russian segment in the Orlan spacesuit. So by having he and I go out on that task, he has some familiarity back there that I don't have, and so that's an advantage to us as a team to get out there and do that work.
And this was actually in the plan for the summer of 2010 and got delayed because of a different issue on the station.
Right. It got pushed off, so it fell, and that's not uncommon for the stuff to roll downhill and land on the next point of opportunity, which happened to be us.
And that's going to be your task for the entirety of EVA-3?
It is essentially, that's the main task. Although we have some other cable routing, which we're calling Y cables, for lack of a better word, but they're essentially 2 cables that have a Y split in them. They're fairly long, but they also are strung along the Russian module and part of the U.S. Module, right where the connection's made with the node, what we call node 1, and the Russian module. And these are redundant power supply cables for the Russian segment. So we're going to install 2 of those and allow provide the capability for redundant power supply to the portions of the Russian segment.
Okay, then the last EVA, number 4, this would be Mike and Greg going outside. What's on the schedule for the last EVA?
And Greg is going out first for that EVA, and that'll be the second of his spacewalks, the third for Mike Fink. And the primary focus of that EVA is to leave the space shuttle boom, the OBSS, the device that we use to extend the capabilities of the space shuttle robotic arm. That lives on the starboard side of the space shuttle payload bay, and when we do inspections of the belly of the orbiter, we use the robotic arm to take that boom out, and it's got some cameras on the end of it, and we use it to extend, what the capabilities of the arm are as it looks around the different components of the shuttle. We're going to leave that boom on space station just in the case that the space station ever has need for a extended Canadarm2. If for some reason they want their arm to be longer, this device will be on the space station. We will change the grapple fixture that's on the end of the boom. Right now it's designed to accept the space shuttle robotic arm, but we're going to put a new fixture on the end, which is again one of these power data grapple fixtures, PDGF, the same component that we're putting on the Russian segment. We're going to apply one of these devices at the end of the boom and leave it resident on the space station in case the station arm wants to use the boom.
Tell me about where it's going to go and what it takes to prepare that site.
It will live, it's been left one time before. I believe STS-123 left a boom on orbit, and it lives essentially right on top of the US segments on the truss. So it's sort of on S0 and S1, so the starboard side, just to the left of the long axis of the space station, up on the truss. And it involves coordination with the Canada arm, the space station arm, to place the boom in a position where Mike and Greg are ready to receive the boom into some, what we call them gun racks, but they're essentially a set of jaws that grab onto fixtures that are on the boom and close down like hands that hold it in place, and they tighten down those fixtures and secure it into place.
So 4 spacewalks is it's a pretty busy.
We'll be busy.
Time for you all. But that's not unlike what you experienced on your first flight.
That's right. On for the STS-125 mission, we did 5 spacewalks, and we didn't have a day in between as a break. I personally did, so I did EVAs 1, 3, and 5 with a day off in between. And on days 2 and 4, I was inside, doing the choreography for the next event. On this mission, of course, we do our spacewalks are days 5, 7, 9, and 11. So there's always a day in between still, but we're not filling that with another team, doing EVAs. So we all sort of get a day off in between instead of just half of the EVA team, which will be nice.
Something else new, during rendezvous and docking, and then again after undocking and fly around, your crew's gathering data for what's called the Development Test Objective known as STORM, which stands for Sensor Test for Orion Relative Navigation Risk Mitigation.
Mm-hmm. I'm glad you knew the full words of the acronym. Yeah, we just call it STORM.
This will include a re-rendezvous with the station after the separation, which is something we've never seen before. Fill us in on what this test is and what you folks will do to support it.
Yeah, I hope, I'm certain Mark Kelly will be able to provide more information as the commander of the flight and helping with the, performing the fly around itself. But essentially what we will do is we will collect data on the original rendezvous. So STORM is a device that uses cameras, essentially, visual navigation systems, to look at reflectors and objects on the space station as we approach, to provide guidance and navigation information to the approaching vehicle. So we have a laptop computer on the flight deck, and it's actually my job to monitor the functions of the laptop computer and report the status to the ground and understand whether or not it's operating in the way that we expect as we're approaching, because what they're going to try to do is use the initial approach data to help calibrate their sensors so that they can relate visual images back to distance and position within the software and the hardware itself. And then when we undock, we'll do the standard space station fly around. So we'll undock, we'll do one loop around, one lap around, and when we get right back to just about where we started from for the undock, then we'll go up around and depart out to something like 250,000 feet or maybe further. But it's quite a ways out on the back side of the space station. And then we'll begin a second approach back into the station, I think to within about 600 feet is the closest we'll get. And on the way back in, they will again collect data on the approach, this time hopefully having already done some calibrations with the instruments because of the initial approach, but also this is again just data collection and calibration of their images further so that in the future if they do additional tests or it's actually used for operationally for the sole navigational inputs, the device and hardware would be ready to go.
And this was with an eye toward future vehicles.
It is. It is. It would be a future rendezvous system for whatever wants to utilize that system.
STS-134 is the last scheduled flight of Endeavour, still gathering data on new, for new vehicles even as we go.
It is, yeah.
What are your thoughts about this shuttle's place in the history of human spaceflight and the work that's been done in the shuttle program?
You mean Endeavour or the
Yeah.
shuttle overall?
Both.
You know, all of the vehicles are special and unique, and they've all flown their, you know, really just a small complement of what they were designed for. Maybe not in years, but certainly flight life, they were all designed for 100 missions, and we're seeing, you know, mid-30s missions out of, I think, each vehicle. You know, my only experience on a spacecraft previous to this was Atlantis, and it was a great space shuttle. It did its job, and we flew back. I'm sure Endeavour will perform just the same way, and they've all done very unique things, just, you know, just as the shuttle program itself has done special and unique things for us in history. So, you know, my own feeling is that yes, indeed, it's time, if we're going to change our focus from low Earth orbit. The shuttle has done its job in building the space station. It would be desirable to have a plan that was overlapping, or some capability that was overlapping with the space shuttle. It doesn't look like we're going to be there with the U.S. or NASA-based program, but I suspect that we will get there in a matter of time. May not even be, you know, in my career. It may not. I'm assuming it'll be in my lifetime, but you know, I don't think we're going to stop exploring or flying in space because we're retiring the space shuttles. It's certainly done a great job up till now.
You're going to be flying this mission right around a couple of significant anniversaries. You got on April 12th, the 50th anniversary of the first human space flight, and the 30th anniversary of the first shuttle flight. And then in early May, the 50th anniversary of the first American space flight. What are your thoughts about you being in space right around the time that these things are being commemorated?
You know, maybe it's fitting if 134 you know, remains as the final space shuttle flight. Maybe that's the appropriate time to fly it, is when we're marking the anniversary of all these other great beginnings in space flight. We'll mark a great end, which will hopefully lead to another great beginning. You know, I don't think we're going to stop exploring. I don't think humans are capable of not exploring, especially outer space. We look up into the stars every night and wonder what's up there.
Things have changed an awful lot in the 50 years since Gagarin and Shepard flew. Look 50 years in the future and tell me where you think we're going to be then.
I think we'll be on Mars, or at least have gone to Mars. And I hope that we will have the capability for sustained presence on the moon, and that we will be utilizing the resources that we think are there, that we know are there, and those that we have no idea are there, but they're just waiting for us to go and you know, take advantage of them and utilize what we have as our nearest neighbor.